Hello, knowledge seekers. In this episode of 20-Minute Books, we delve into the complex world of our body's internal protectors with An Elegant Defense, written by Pulitzer Prize-winning author Matt Richtel. Published in 2019, this book is an insightful journey into the intricacies of the human immune system, presented through a blend of scientific knowledge and the poignant story of a cherished friend. Matt Richtel, celebrated for his contributions to the New York Times and an accomplished author of gripping novels such as Doomsday Equation and Dead on Arrival, uses his expertise to unravel the mysteries of what he describes as our most elegant defense mechanism. This book is perfect for those who are intrigued by the sophisticated workings of the immune system and its role in maintaining our health. Immunology students in search of a comprehensive yet easily understandable guide to the immune system's functions and complexities, and any individuals aiming to enhance their well-being. An Elegant Defense not only enlightens curious minds but also provides a heartfelt perspective on the human experience intertwined with medical science. Join us as we explore how our bodies defend, protect, and sometimes betray us in this illuminating episode. An Elegant Defense, The Extraordinary New Science of the Immune System, A Tale in Four Lives. Introduction. Unlock the secrets of your body's guardian, the immune system. Matt Richtel was propelled by a moment of awe. A friend's life, hanging by a thread, was dramatically saved by an innovative drug that animated the immune system into a potent force against cancer. This profound experience set Richtel on a quest to unravel the mysteries of the immune system and share its wonders in his book, An Elegant Defense. This extraordinary narrative takes readers on a journey that captures the evolution of immunology, the medical discipline focused on our body's complex defense mechanisms. But Richtel presents this history with a twist, intertwining it with the real-life medical sagas of four individuals, each reflecting pivotal moments in the advancement of immunological science. Let's embark on a whirlwind exploration of immunology's rich tapestry and hone in on one narrative in particular, that of Jason Greenstein, whose experience serves as a beacon, illuminating both the remarkable achievements in harnessing our internal defense system and the boundaries that still confine our control over this intricate biological machinery. As we navigate the depth of this narrative, you'll gain an appreciation for the varied roles and remarkable functions of immune cells like neutrophils and dendritic cells, the historical animal studies that charted the path to our current understanding of the immune system, and why an immune response that goes into overdrive can be just as perilous as one that falls asleep at the wheel. Part 1. Inside Your Body's Festival. How Your Immune System Keeps the Peace. Picture the most vibrant festival imaginable, pulsating within you, a never-ending celebration teeming with your own body's cells and countless bacteria and viruses. Yes, this bustling metropolis of microscopic life, which the author dubs the Festival of Life, thrives inside each of us. At the helm of this buzzing fiesta are the dedicated caretakers of your well-being, the immune cells. Imperceptibly small yet immensely powerful, these cells operate like a finely tuned security force, attending to cellular mishaps, purging harmful toxins, and combating invaders called pathogens. Pathogens, the scoundrels of the festival, manifest in three primary guises: bacteria, viruses, and parasites. Here, we'll cast the spotlight on bacteria and viruses, the two rampant mischief makers of illnesses. These pathogens are microscopic menaces. A few thousand bacteria can huddle within a single human cell, and viruses even manage to squeeze into bacteria by the thousands. But let's be clear, not all bacteria and viruses are villains. In fact, only about 1% of bacteria pose a threat to health. And viruses? Some of our very own genetic code owes its creation to retroviruses, which infiltrate human cells and integrate into our DNA. But, lest we forget, among the harmless many lurk the lethal few. The bacterium Yersinia pestis unleashed the Black Plague, ravaging 14th century Europe. Joining its ranks of infamy are Salmonella, E. coli, and Tetanus bacillus, alongside an infamous list of viruses like Ebola, HIV, and the flu. Turn the clock back to the pre-1900s, and you'd witness viral and bacterial infections like influenza and pneumonia reigning as merciless executioners, ravaging populations. Yet in our era, the threat of such pathogens has dwindled dramatically. How did humanity turn the tide against these microscopic marauders? For that, we'll delve into the thrilling saga of immunology, the science behind our internal legion of guardians. Part 2. Unraveling the mysteries that sparked the birth of immunology. At the heart of immunology lie three extraordinary puzzles that unfurled across the centuries: a perplexing organ in a chicken, peculiar veins in a dog, and an uncanny observation in a starfish. These bewildering finds would ultimately shepherd scientists into the uncharted territory of the immune system. The journey begins with a 16th century Italian anatomist, Fabricius ab Acquapendente, who, as he anatomized a chicken, stumbled upon a peculiar organ nestled beneath its tail. Resembling a small pouch, the function of what he dubbed the bursa remained an enigma. Fast forward to 1622, and another Italian, Gaspare Aselli, during a canine dissection, lays eyes upon milky veins in the animal's stomach, a confounding sight in an age when blood was believed solely red. What purpose could these atypical veins serve? It wasn't until 1882 that a piece of the puzzle clicked into place, thanks to a Russian zoologist named Elie Mechnikov on Italian soil. Peering beneath his microscope at starfish larvae, he discerned wandering cells meandering within them. Could these cells be more than aimless drifters? Could they, in fact, be guardians patrolling for intruders? Mechnikov's curiosity led to an experiment involving rose thorns, starfish larvae, and a hypothesis rested on vigilant cells defending against invasion. By dawn, his theory bore fruit. The cells had converged on the thorns, devouring the damaged tissue in a process we now call inflammation. But the mystery persisted. How did these cells discern an invasion? This enigma, alongside the baffling findings in the chicken and dog, laid the cornerstone for the blossoming field of immunology, driving fervent pursuit to decode our body's inner sentinel. Part 3. The Thymus Revealed. Unlocking a hidden player in the immune system. The late 1950s bore witness to an unsettling series of events in a London laboratory, where French physician Dr. Jacques Miller found himself amidst a crisis of expiring rodents. Each post-mortem unveiled startlingly similar symptoms: a liver besieged by lesions, indicative of a ferocious infection. But why this unfortunate fate for the mice? Enter Dr. Miller, whose surgical inquiries into an enigmatic organ known as the thymus would soon catapult it onto center stage in immunological studies. In the post-war era, as leukemia cases soared in the aftermath of atomic warfare, researchers turned vehemently to mouse models. By inducing cancer through radiation, they hoped to gain insights that could assist the afflicted in Nagasaki and Hiroshima. Notably, some mice developed leukemia naturally within the confines of their small chest-set thymus. Dr. Miller, engrossed in leukemia studies since the early 50s, was on the brink of unveiling the thymus's pivotal role. During his experiments, when he injected cancer-laden filtrate into both infant and adult mice, only the infants succumbed to leukemia. This discrepancy set the stage for deeper investigation. By meticulously removing the thymus from newborn mice, he unleashed a sequence of events that would steer his research to a groundbreaking conclusion. Administering a juvenile thymus to an adult mouse, post-leukemic filtrate injection invariably triggered leukemia. This observation, layered with the vulnerability of thymusless infants dying from rampant infections, led to an epiphany. The thymus was no redundant organ, but rather a linchpin in the body's immune defense system. Part 4. the pivotal role of the thymus in defining self from non-self. Delving into the inherent complexities of the body's immune response, Dr. Jacques Miller faced the intricate question of identity. How does the body discern between its own constituents and foreign invaders? Despite the murky waters of knowledge during his time, one thing was clear. The immune system possessed the remarkable ability to discern self from non-self, although this trait sometimes led to confusing friend with foe. Skin grafts commonly ended in rejection, a cruel testament to the body's inability to embrace non-native tissues. This phenomenon, known to clinicians, provided Dr. Miller with a hint to solidify his hypothesis about the thymus's instrumental role in immunity. Experimenting with mice, Dr. Miller noted that typical mice with intact thymuses rejected skin from other mice. In stark contrast, mice without thymuses accepted grafts without issue, even sporting coats of multi-hued fur from multiple donors. The equation emerged: presence of the thymus signaled rejection. Absence resulted in acceptance. Blood analysis of these thymus-deprived mice spotlighted a glaring scarcity of a particular one-nucleus-containing lymphocyte. Miller attributed the origin of these cells to the thymus, thus christening them thymus-derived cells, or T cells in short. The looming query still persisted. How do T cells distinguish and eradicate pathogens? A historical hypothesis by immunological forefather Paul Ehrlich in 1891 proposed that certain cells harbor side chains, essentially biological keys, matching up to locks, the antigens on pathogens. Once connected, the body could mount an attack, and Ehrlich denoted these keys as antibodies. Dr. Miller speculated he had uncovered the key bearers central to immune operations. And while his hypothesis echoed Ehrlich's insights, the underlying reality would prove to be an even more intricate and marvelous biological tapestry. Part 5. The puzzling evidence pointing toward multiple types of lymphocytes. By the mid-20th century, the bursa, once a cryptic organ shrouded in mystery, was thrust into the spotlight of scientific intrigue. Its crucial role in generating antibodies was unveiled when a researcher observed that chickens missing their bursa suffered a stark decrease in antibody production. This discovery was particularly significant as it tied back to a stark revelation from earlier in the decade. A dearth of antibodies spelled disaster. This link between antibodies and health was dramatically highlighted by the case of a young boy at Walter Reed General Hospital, whose inability to produce antibodies led to a relentless onslaught of infections, including recurrent pneumonia. While antibodies were known to be associated with lymphocytes, vital one-nucleus blood cells, the boy's medical situation presented a vexing puzzle. Even with a normal thymus, an ample supply of lymphocytes, and some defensive capability against viruses, his immune system was failing him. The question loomed: what was the missing piece in his immunological jigsaw? The mystery persisted into the 1960s, whereupon physician Max Cooper probed into Wiskott-Aldrich syndrome, a rare condition that left patients highly infection-prone due to ineffective immune responses. Autopsies revealed individuals with this syndrome had ample lymphocytes and intact thymuses, deepening the riddle. It was Cooper's sudden insight that cracked the case wide open. He hypothesized the existence of not one, but two distinct kinds of lymphocytes, each with a separate genesis. With Dr. Miller already having established that T cells hailed from the thymus, there had to be another type of lymphocyte with a different birthplace. If you're intuitively gesturing towards the bursa of Fabricius as the source of this other lymphocyte variety, prepare for a slight letdown. Humans, it turned out, lack a bursa altogether. Part 6. The dynamic duo. T cells and B cells, your immune system's sharpshooters. Through tireless experimentation, Dr. Jacques Miller corroborated Dr. Max Cooper's theory, unveiling that the human body houses two specialized types of lymphocytes, T cells, and their newfound counterparts, B cells, offspring of the bone marrow. Together, these cells account for a formidable 40% of our white blood cells and form the crux of our immune system's precision defense force. To illustrate their roles, let's say the flu virus has infiltrated your system. In the initial onslaught, various cells representing the remaining 60% of your white blood cells converge on the infection, a chaotic battle mirroring Eli Mechnikov's observation of cellular response in starfish larvae. At this juncture, the enemy isn't identified with precision, a job reserved for the T cells and B cells. T cells are bristling with receptors resembling spikes that roam in search of familiar foes. Upon recognition, a T cell might engage the pathogen directly or delegate the task to B cells. B cells, armed with surface-bound antibodies, think of them as bespoke antennas or keys, embody Paul Ehrlich's century-old side chain theory, each uniquely keyed to match a singular antigen, the unmistakable signal of an invading organism. Imagine the body as an expansive battleground where B cells traverse tirelessly. Many may spend a lifetime aimlessly wandering without ever encountering the elusive lock their built-in key is destined to open. So, in the midst of your battle with the flu, picture a diligent B cell toting the exact antibody that fits the flu virus's antigen. Once they collide, it's a cataclysmic lock-and-key moment. The bond triggers the B cell's fury to demolish the virus or rally further cellular reinforcements. And while you may wonder how our bodies mastermind the creation of such a diverse and precise antibody repertoire, brace yourself. The explanation behind this immunological wizardry is nothing short of astonishing. Part 7. The genius behind the immune system's infinity machine. Transcend the boundaries of the known world. Take a plunge into a foreign lake and introduce your body to a bacterium it's never met before. Its unique antigen is a stranger not just to you, but to the lineage of your entire kin. How, then, does your body miraculously have a ready antibody to confront this novel invader? Enter Susumu Tonegawa, a Japanese scientist who cracked this enigma in the 1970s while working at the Basel Institute for Immunology. He uncovered a marvel that the author dubs the infinity machine. The conventional wisdom of the time told scientists that if you scrutinized a specific genetic segment of an organism, a T cell for example, it would align identically across all T cells. When Tonegawa applied this logic to developing B cells, the initial findings were as anticipated. The genetic sequences of immature B cells were carbon copies of one another. The eureka moment arrived when Tonegawa juxtaposed immature B cells with their mature counterparts. The genetic sequences had undergone a transformation, a phenomenon exclusive to B cells. Why is this remarkable? Here's the crux. Although immature B cells share a fundamental genetic script, a vast array of additional genetic codes accompany them. In the journey to maturity, B cells indiscriminately discard chunks of this surplus genetic code, but each cell abandons a unique set of genetic pieces. This genetic honing manifests as a finely tuned system capable of spawning trillions of distinctive antibodies. Our metaphorical lock and key sees a renaissance here. B cells bear keys so obscure and specialized that some locks may be purely theoretical. Through this prodigious mechanism, this infinity machine, our bodies arm themselves with a near limitless arsenal of solutions, prepared for the infinite battles against pathogens that our ever-changing world presents, plus a multitude of hypothetical challenges that may never arise. Part 8. Navigating the dual layers of our immune system. A microscopic battle rages within when pathogens infiltrate your body, and understanding how your immune defenses synergize to combat these invaders is crucial. It all begins with the non-specific or generic response, complemented by a highly targeted strategy. Picture the front line of defense, the phagocytic cells, those vigilant patrollers first discovered by Eli Mechnikov. Among them are the neutrophils, accounting for a hefty slice of your white blood cells. Like magnets, they're drawn to the source of infection, where they launch their attack, injecting enzymes that lay waste to the invaders. In a final act of sacrifice, the neutrophils dissipate, leaving behind the substance we know as pus, a collection of their dissolved remains. The aftermath of this initial offense involves a cleanup crew of other cells, disposing of the detritus of battle. Parallel to this chaos, the specialized defense mounts its campaign. Here, dendritic cells, adorned with branch-like extensions, ferry pieces of the offender to T cells for analysis. It's a decisive moment. Either the sample is recognized as harmless, or it triggers alarms that marshal a customized response. Alternatively, the intruder might directly cross paths with a T cell or B cell. This moment, where a pathogen's antigen meets the cell's receptor, like a puzzle piece slipping into place, prompts a precision assault. The immune system swiftly trains a team of specialized agents to tackle the threat. Yet, a conundrum looms. How do T cells and B cells discern allies from adversaries? While B cells are equipped with antibodies to potentially latch onto myriad antigens, not all of those antigens signal danger. Some belong to beneficial bacteria. The resolution to this dilemma emerged in the 1990s with the work of researchers Ruslan Medzitov and Charles Janeway, who illuminated our possession of not one but two immune systems. You've become acquainted with the adaptive immune system, which learns and memorizes pathogen faces to combat future encounters more effectively. Yet, this adaptive expertise lacks context without cues from the innate immune system, which recognizes universal hallmarks of pathogenicity, such as specific nucleic acids or signature molecules found on hostile bacteria. The linchpin of the innate response, the toll-like receptor, stationed on various cells, including dendritic cells, capable of discerning these universal danger signs. Upon confirmation of an enemy presence, this receptor sends out an alert, and T cells, akin to seasoned generals, command a strategic retaliation to vanquish the threat. Part 9. The body's own communication network, cytokines and immune response orchestration. You're on the brink of becoming an immune system aficionado, but let's dive into one more pivotal aspect: how cells communicate to orchestrate a defense. This biological hotline hinges on a protein known as a cytokine, the body's version of a text message or signal flare. When pathogens breach defenses, the cells nearest to the invasion broadcast an alarm by releasing cytokines. This alert can ripple across the entire body in a matter of hours, mounting a coordinated defense. Cytokines essentially act as the message itself. Consider the mighty interferon, a type of cytokine that swoops into action when a virus invades. Upon detection, infected cells deploy interferon to thwart the virus's ability to multiply. Nearby healthy cells receive this signal and start churning out their own interferon, creating hostile conditions for the unwelcome guest. However, interferon's battle tactics come with collateral damage, manifesting in familiar symptoms: the aches, fatigue, and fever that accompany a typical viral infection. Surprisingly, these are not the virus's dirty tricks, but rather the interferon's strategic maneuvers, prompting you to rest and enabling the body to rally its forces. Yet, not all cytokines signal an all-out assault. Some, the regulatory cytokines known as interleukins, actually dissuade the immune system from escalating its response. Fine-tuning this complex system is crucial. The immune system cannot simply obliterate every organism in sight. That would render the festival of life a ghost town. It must finely discriminate between friend and foe, launching precision strikes on harmful entities while sparing the innocuous or beneficial. Troublingly, some pathogens have mastered the art of immune manipulation, turning these very signals against us to forward their own sinister agendas, as we'll explore in the next segment. Part 10. The Fierce Battle. Jason Greenstein's Fight Against Hodgkin's Lymphoma. Let's step into the world of Jason Greenstein, an old friend of the author, known for his zestful spirit and tenacity both on the basketball court and in the eclectic realm of entrepreneurship. Yet, in a heart-wrenching turn of events, Jason faced a formidable challenge far removed from the playing fields and business ventures of his youth: a diagnosis of Hodgkin's lymphoma, a cancer targeting the very system tasked with defending him. Hodgkin's lymphoma doesn't just strike any part of the body, it infiltrates the lymphatic system, the vital network where immune cells are marshaled and dispatched. It's where your lymph nodes operate as hubs of immunological activity, situated in vulnerable spots like under the jaw or in the armpits. This devious cancer creeps into the lymphatic highways by commandeering B cells, twisting them into rogue elements that manipulate your body's defenses by masquerading as friendly forces. Each T cell contains a self-destruct mechanism termed the PD, or programmed death receptor. It's a necessary function, allowing T cells to eliminate themselves when the need for immune balance outweighs the call to fight. But Hodgkin's lymphoma turns this mechanism into a weapon with its PDL1 ligand, molecules that bind to the PD receptor, like a spy whispering a lethal command to unsuspecting guards. The cancer cells, disguised in B-cell clothing, drift undetected throughout the lymphatic system, triggering a wave of T-cell self-sabotage, effectively dismantling the immune system from the inside. Fortunately, most find solace in the arms of chemotherapy, which boasts a 90% success rate against this type of lymphoma. Unfortunately, Jason found himself among the scant 10% for whom traditional chemotherapy offered no salvation. Part 11. Jason's valiant struggle and the double-edged sword of immunity. Jason Greenstein's resilience was undeniable. He endured rounds of chemotherapy and even a bone marrow transplant, sealing the fate of both the malignant and healthy B cells. And yet the cancer returned, undeterred. The treatments had taken a heavy toll. Jason was neutropenic, his first-line immune warriors dwindled to a critical low. His vigor drained, contemplating surrender seemed more appealing than enduring, another fight with an already ravaged body. But then the tides turned with the introduction of nivolumab, a trailblazing drug that hadn't yet cleared for Hodgkin's lymphoma. This drug didn't just neutralize the cancer's deceptive calls for T-cell suicide, it reprogrammed the immune cells to become assailants against the malignancy. The odds were against Jason, with survival expectations as bleak as 1 in 12 million. Nevertheless, he defied these odds. A month on nivolumab saw his bulky back tumor vanish, shedding 15 pounds, the weight of the excised malignancy. Within 6 weeks, he was ushered into a state of complete remission. It felt like a beginning, but for Jason, it marked the final chapter in a story too complex for closure. Emboldened by his remission, Jason underwent a procedure to implant his sister's stem cells, an act that gifted him an entirely new immune system. The first rays of hope shone through, followed by encroaching shadows. What began as minor complications burgeoned into catastrophic system failure. Jason's liver gave out just over a year post-nivolumab, signaling his immune force's mutiny against his own organs. The ensuing inflammation spiraled into a cytokine storm, an unrestrained, devastating immune overreaction. On August 10, 2016, Jason's last breath was stolen by the very mechanism designed to preserve life. An immune system unmoored, a defender turned destructor. There might not be a clear-cut lesson in Jason's narrative, but one truth emerges resolute. Our immune system holds astonishing power, capable of healing or bringing ruin. Its profound reach commands our awe and necessitates cautious consideration when we wield its might, lest we become victims of the very force we seek to master. Final summary. Our journey through the enigmatic and powerful realm of the immune system reveals a delicate dance between defense and destruction. While a robust immune response safeguards us against relentless pathogens, when the scales tip too far, it has the potential to become our own worst enemy. The odyssey of immunology, rich with discovery and innovation, has set the stage for groundbreaking treatments capable of mobilizing our internal army against diseases once thought unbeatable. The contributions of early visionaries and modern scientists alike have expanded our understanding of this complex internal guardian. Yet, despite significant leaps in knowledge and technology, the quest to harness and direct our immune system remains an ongoing challenge. As we stand in awe of the profound power and precision of our elegant defense, it's evident that the interplay of aggression and restraint within our immune system is not just a scientific curiosity but a matter of life and death. Thank you for joining me today on this journey of learning and discovery as we explored the insights of another thought-provoking book in our growing library of knowledge. If you've enjoyed our time together, please take a moment to follow our podcast, give us a 5-star rating, and share 20-minute books with other knowledge seekers. Your support truly means a lot. Don't forget to join me again in the next episode, where we will delve into another enriching book. Until then, happy reading and happy listening.